So hello everyone. Today we record the lab recitation for week 4 with Python in Math 102. So I'll share with you my first of all my presentation, and then we'll go to the Python 5. Okay, here we go. So the outline of the presentation will talk about the solution of the exercise of week number 3. And then we'll follow the substitution rule and finish with an exercise for next week. So the exercise from last week, week 3, this is the exercise, a little bit of modification with respect to the exercise you had on the previous slides. So there is a note that says the original exercise was modified as there are no algorithm implemented in Python that could solve the part 2 of the question. It's a bit complicated because of the AX. And maybe it's too much to tell you for now, but still there is a numerical solution, but it's not exactly what we want. So the modified solution question is like this. Let's consider f of x, which is 2x squared plus 2x. On the interval 0, 2, there are two sub-questions. We'd like to find the average value of f, and then find c such that the f average is equal to f of c. So, of course, you will upload the week 4 solution file, and then we will go to the Python file. So let's start with the first slide about this exercise. So there are some parts in this question. The first part, we here need to define the variable x and the function f, and display it and find the integral from 0 to 2. And this is exactly what is done here. So mainly to give you a quick idea, again, we import the NumPy and the SymPy packages as NP, SMP. We also import from SymPy the symbol, capital S, the function, capital F, the lambdify, the square root, the exponential, and the integrate. Maybe they are needed. And then we also define the X symbol. So X as a variable, F as a function. And now F is 2x squared plus 2x. We'll display F, and we'll set the limits of our interval here with A equals 0, B equals 2. And we also integrate F from A to B, so from 0 to 2. And we already seen that before. So of course, the antiderivative of 2x squared plus 2 is going to be a cubic function. And we will evaluate it from 0 to 2. The final outcome here would be 28 over 3. So after this, we'll move to, and this is exactly what is done here, by the way, in the Python file. So here we go. Here is our Python file, the sub window. Okay, and this is exactly what is done here. Okay, make sure if you do Shift Enter, you should be able to re-execute the code you have there. And I strongly advise that you try to learn this by heart. Okay, avoiding spelling mistakes and stuff like this. Then we have a second part in this exercise. We move to slide number 3 from this exercise. And here, the second part, we first of all need to compute the average value of the function. And we have to make sure that b is greater than a before doing anything. So if the condition is not met, we print an error message. This is to make our code more interactive with the user. So in the coding part, let's define delta to be equal to 0. So this in fact initializes the variable delta. And if b is less or equal to a, that's a condition, we will print the error message, error value of b is less than a. Okay, else we'll compute the value of delta, which is b minus a, and we'll compute the average value, which is the value we got from the previous slide, which is the 28 over 3 divided by delta, and we'll display it. So here, of course, here the solution was 28 over 3 divided by 2. We expect to have 14 over 3, and that's exactly what we have here. Okay, so this is what we have in the code part. That's in the code part, that's what we got. Okay, then the next part example, we need to find the C that makes the value of f of C equal to the average value of f on the interval AB, on the interval 0, 2. So let us find this. So to do that, we need to define C as a symbol, again, using SMP symbol, S capital. And we will solve the equation using the solve equation here function we've seen already by substituting C in F. So we use the subs function we've seen already in the first week, minus average for the value C. So here what this does, it finds the 0 for this equation. F of C minus average equals 0, and solves with respect to C. Now, notice that's very important that the solutions to this equation are going to be entered in this variable. In fact, it's a solution list. So list, I call it, solution list. And we will display the so list. And as you see, after the execution, we have this display. So there are two solutions, minus 2 square root of 3 over 3 and plus 2 square root of 3. So there are two elements in so list. Okay, which one? Now the question, which one belongs to 0, 2 and to the interval 0, 2? And to be able to know that, instead of guessing and try to check out which value is in 0, 2. Of course, here it's obvious that is one of them that is negative. The other one is probably less than 2 and greater than 0. But we can also automatize this because we may face this problem many times and having more than 2 roots inside a single interval. Okay, so the Python part is here. Okay, that's for the value of f. That's here. Here we solve it, and we found the two roots inside the 0, 2, and then we need to find out which one belongs to the interval 0, 2. So to do that, we will have to learn a couple of things, and here I review with you the things we need to learn from this week's class. So first of all, solutions accepted should be between 0 and 2. And we need to automatize this and display only acceptable solutions. So we will use a for loop to read through the elements of SOLIS. And the command length here, the function length or this syntax length, gives the length of SOLIS here. And it's important to learn how to write a for loop or an if condition like we've seen in the previous slide. So we have to always be careful with the indentation when you write a for loop or an if condition. And here is the coding part where we automatize the reading of the elements of the SOLIS. So we'll say for I in the range, and here between brackets, length of SOLIS. So here there are two elements in SOLIS. So the length of SOLIS is 2. So here I will go from 0 to 1. Always the maximum range will stop at n-1. Okay, so if SOLIS is greater than 0, that's the condition, and that's for end. SOLIS of I is less than 2, and of course I is iterating here. So we'll start with the first element. The condition is not satisfied because it's negative. The second element, which is 2 square root of 3 over 3, is between 0 and 2, of course, then we'll display. So we will display the possible value of C, which is SOLIS I. And this way we have directly access to the value that is inside the interval, and that's what we needed. So the code part is here, and here's the implementation, and that's the for loop we have. And the I is displayed, so we can know which item we are reading, and we'll display the value of SOLIS at I. We added here some part, some indication, and if SOLIS I is greater than 0 and less than 2, we'll display it, and of course the value that is displayed is for the first one is -2 square root of 2, -2 square root of 3 over 3, it is rejected. And the second one, when I equals 1, we will understand that we display 2 square root of 3 over 3. Why did I do this? Why am I displaying the value of I? Because you need to know that when we are reading a list here, we start with a 0 at the first element. So the index of the first element is 0. Second element is not 2, it's 1, since we start from 0. And it goes on like this. Okay? So that's very important to record for our midterm evaluation. Now we start the material for week 4. And this part of the material is about what we call substitution rule, which corresponds to section 5.5 from your textbook. So there are many examples inside this exercise. We need to integrate arctan of x squared over x squared plus 1. Then 5 to the power x, sine of 5 to the power x. Then 1 over 1 plus root of x all to the power 4. And then finally x times root of x squared plus a squared, where a is a constant. So for the first subpart here, where we're talking about the arctan of x squared over x squared plus 1, we will define x as a variable using the symbol function from SMP as usual. And here, to me, I'm calling y1 to be what is returned when I enter this function. SMP a tan of x squared. What is a tan from SMP? That's the arctan function. A tan of x is the arctan function, squared, of course, all of it, divided by 1 plus x squared. Don't forget the brackets. We'll display here y1, so that's the expression of my function, and I'll integrate it using the integration, of course, comment. Of course, you can add a constant of integration. We've seen that 2 weeks ago. So that's the main part here. A tan cube of x divided by 3, that's my antiderivative, basic, plus you may add plus c if you wish, like we did 2 weeks ago, okay? So then we have the sub-questions B and C. The first one is about the integration of 5 to the power x times sine of 5 to the power x. Of course, you remember sine function from SMP is sin, S-I-N. We'll display y2 here. So that's the second function to be integrated, and we'll integrate it again. And the result is minus cosine of 5 to the power x divided by ln of the hive. For the C part, it's y3, which is equal to 1 plus square root of x all to the power 4 in the denominator. That's y3. We integrate it, and we get this beautiful mathematical beast. Okay. Then we'll move to the last question, which is D. Before I show you the Python file, in the example D, we need to define a symbol A, because the function that needs to be integrated is x times square root of x squared plus a squared. So A, it's normal that it should appear in the antiderivative, and here we'll define it as we defined x as a variable. Okay, and here y4 is x times square root of x squared plus a squared. We'll display y4 and we'll integrate, and of course a would appear in the antiderivative here, which is a squared times root of a squared plus a squared over 3 plus x squared times a squared plus square root of a squared plus x squared over 3. And guess that we needed here to specify the variable of integration, and that's why this example is here, because you may consider that there are two variables of integrations, x of and a, and here we needed only the integral with the integration with respect to x. So we need to specify the variable of integration. For the code part, of course, here is the code part. So there are many parts in this example. Here are the solutions of each one of the sub questions. That's the A part, the integral of a tan arctan squared of x divided by x squared plus 1. The integral of 5 to the power x sine of 5 to the power x. The integral of 1 over 1 plus square root of x all to the power 4. And finally, the D part, where we needed to specify the variable of integration. And here we go. So y4, the function to be integrated is x times square root of x squared plus y squared. And here we specify the variable of integration. Okay. Okay. So now we go back to our slides. We have a second example, and here we need to make a substitution. And here in this substitution, we need to substitute 3x plus 5 by u. Our integral is from 0 to 2, x over root of 3x plus 5. To be able to do the substitution, we need to use the transform command. And that's the coding part here on the right part. And we define the integral. That's a new command, integral with capital I, where the function is directly there. And we need the second part of the syntax, or the integral command, is the interval of integration. So that's I. And to be able to do the substitution, we'll define k, which is the new integral that transforms I, the first integral, using this substitution, which makes 3x plus 5 equal to u. So once you display the first integral, this is I, what we call small I, and this is the new k, which is after the substitution, the new integral. So now u is integrated from 5 to 11, and that's normal because x was from 0 to 2. Okay, and that's the new integral. What's the purpose of doing this? This new integral is much easier to integrate, at least manually. Of course, we're not talking about the Python evaluation part, but it's important that you need to know how to use the substitution. Okay, that's the coding, the slide part. The coding part is here, as usual. The transform is there. So that's how we use the transform command to substitute 3x plus 5 by u. And this substitutes the x plus 5 by u and change the limits of integration accordingly. And we display both. Okay. You can make it much better. You can just using this new command, which is simplify. What is the purpose of simplify? Simplify would give you directly the value of k, because k is a definite integral. So this is exactly the value of the integral, minus 8 square root of 11 over 27 plus 20 times root of 5 over 27. Okay. So that's for the second example. The last thing we will see today is the exercise for next week, which is taken from Larson Calculus book, page 342, section 5.5, exercise 69. We need to find the indefinite integral by making a substitution here, a change of variable. Okay, so that's it for today. Thank you very much. Okay, so we will record next week, hopefully, and good luck.